Hello everyone. So previously we had discussed on the Hungarian algorithm, right? So today we'll be discussing on the topic Hopcroft Karp algorithm, right? So let's see what the definition part say here. Let's get into the definition part. The Hopcroft Karp algorithm is an efficient algorithm just to find the maximum matching in the bipartite graph, right? So it is the efficient algorithm to find the maximum matching, right? So this is also known as maximum matching algo as well, right? So usually they call it as like Hopcroft Karp, this one maximum matching algorithm itself, right? So the Hopcroft Karp algorithm is an efficient algorithm just to find the maximum matching in the bipartite graph, right? It improves over the simple augmenting path approach. Again, it improves over the simple augmenting path approach, right? By finding the multiple augmenting paths simultaneously. It improves over the this one, simple augmenting path approach by finding the multiple augmenting paths simultaneously, achieving a time complexity of because of square root of v plus v into e, because of square root of v into e, right? So let's get into the definition part one. So this is very important, right? So the first part here would be a bipartite graph consisting of two disjoint sets of vertices. Say, suppose let's consider U and V, where edges only connect vertices between the sets, not within the set, right? So this is one thing. Now, a matching is a set of edges. When I say matching, the matching word, it is a set of edges such that no two edges share a vertex, right? No two edges share a vertex, right? So this is fine, I believe. The maximum matching is the matching with the largest possible number of edges. Again, the maximum matching is nothing but the matching with the largest possible number of edges. The Hopcroft, this one, Croft Karp algorithm uses the BFS plus DFS strategy. BFS and the DFS strategy. It will make use of the, so we will be making use of the BFS along with the DFS within the algorithm, right? Both. Right. BFS is nothing but breadth first search to the layer, the graph, and find, we will be finding all the shortest augmenting paths. And for DFS, when we'll be making use of just to augment along these paths in the parallel, right? So we'll be making use of BFS and DFS both. By processing multiple paths at once, it reduces the redundant searches. Yeah. So this is one of the biggest advantage. By processing multiple paths at once, it reduces the redundant searches, making it much faster than a naive augmenting path algorithm. Right. Yeah. Now let's try to implement the same thing in the form of code or the algo, right? So for this one, I have already written, I actually did practice this one. So I just wanted to, this one, what do we call? Um, didn't want it to type, right? So this is fine. Now let me explain this algorithm one. First, what we have done here, so we are importing the this one, fine, DQ basically. This is fine. Now this one class, this is nothing but the Hopcroft Karp algorithm. This one, what do we call class? This is fine. This is nothing but the initialization part of the constructor part. So I have mentioned here. See, this is nothing but the U and V. This one edges. So pair this stores the matched vertex and V for you, and this one pair V. This stores the matched vertex and U for V, right? So this is distance label, right? So this is distance label for the BFS. So we'll be going with the BFS, and we have to go with the adjacency list anyway. Adjacency list for the U, edge U. This is fine. Yeah. Now this method or the function actually add edge function we are making use of, right? This adds an edge from U in capital U to this one, small v in the vertex v, right? So this one, see here, self-dot character, that's what we are doing. We are just adding the edge from U in U to V in V, right? So this is fine. Next part, we are going with a BFS, or we are going with a BFS helper method of the function here. BFS, this one we are making use of the BFS to build layers. This is pure BFS, man. You can just go through this one, right? Also, we are going with a DFS here. DFS, as we had discussed, DFS, this is for augmenting the paths basically, right? So we are making use of the BFS here. First thing, breadth first search. So this one just to build the layers, and this one DFS here, um, it is mainly used to use the this one augmenting paths, right? So depth first search. Finally, we have come to the this one main function here. Main function. Just give me a second here. 1 second. Mm, this is fine. Def is fine. Yeah. We have come to the main. This one. What do we call main method here? Right. So main method of the main function, just to find the maximum matching. So this is used to find the maximum matching. See here. So here we are making use of this one BFS and DFS within the main function. So that is the reason we have written the helper method DFS as well as the BFS, right? So this is fine. Yeah, this is the main function to find the maximum matching. So let's go with the example usage, man. I have went with a simple example usage here. So yeah, so this one here, what do we call? We have went with a Hopman, this one, right? So I have just considered HK here. But so we have went with add edge for adding the edge. We are adding these edges, right? So this is fine, I believe, right? We are going with a 4, 4, right? Nodes actually. So this is fine. So let me draw the graph for this. So I can edge whatever I have written here from 0 to 0, right? So this is fine. 0 to 1, yeah, 0 to 1 and 1 to 1 actually. This is fine. This is, yeah, sorry. We are going with a bipartite graph, right? So let me delete this one. Sorry. This one we have to consider two sets actually. One is U set and another one is V set, right? So this is fine. From 0 we have to 0, right? So this one will go like this, 0 to 0, right? So next we are going with a 0 to 1. So 0 to 1, yeah, let's consider in the same way actually, 0 to 1. This is fine. Then we have to consider from 1 to 1. So from 1 to 1, let me write it in this way, from 1 to 1. This is fine. Yeah. Next, we are considering from 2 to 2 actually. So let me give here 2 to 2. This is fine. Let's consider 3 to 2. For 3 to 2, let me consider in this way. Yeah. 3 to 2. Finally, we are going with a 3, 3. Right. So finally, we are going with a 3, 3. So let's consider here the same actually. 3. So we can just write it in this way. Here we can just write it in this way. So see here, U vertices are on the left here. U vertices. So these are the U vertices. U vertices are on the left, and V vertices are on the right. So this one is V vertices, right? So yeah. Now arrows, basically whatever the arrow I have written here, this basically indicates the this one edges between the partitions, right? So I got confused. Sorry. This is the correct figure, right? So matched pairs are here. We are considering 0, 0, 0, 1, 1, 1, 2, 2, 3, 2, and finally 3 to 3 accordingly with the graph that we have drawn here, right? So this is fine. Now the matched pairs from the Hopcroft Karp, the output has to be from the pairs U actually. I'll just write here pairs U, PU. So from P of U to V basically, and from the pairs V to U. So this one U to V, so you can clearly see here. Basically, we can just write it in this way. 1. So this 1 and U to V, right? 1 to, yeah, 1 we can consider. Again, 1 will be going with, because we have 1 to 1, 0 to 1, 1 to 1. So this one will be 1, 1. The third one would be 2 actually, from 1, yeah, this one 2 to 2. So we have 2, and finally we have 3 as well, 3 to 3. So this one we will be considering 3 as well. So this one from U to V, right? From pairs V to U, we can consider this one V to U we are considering, right? So this one we can consider this one. What do we call? 0. 0 we can consider. This is fine. From B to E. Then we can consider 1 as well. 1, this 1. Next we can consider 2, B to E. Then we can consider 3 as well. So this will be actually double 1, 2, 3 as well as 0, 1, 2, 3. Right. So this is the output that we need to get here. Basically in simple terms. See, U set. So I can just write it in this way. U set as well as the V set. So here 0 to 1 is matched actually. 0 to 1, this is matched. For the matched, I'll just write M here. From 1 to 1 is also matched actually. I can just consider here matched. So this is fine. From 2 to 2 also it is matched, right? So from 2 to 2 also it is matched. So this one I'll just consider M. finally, this one 3 to 3. So this one is also matched actually. Yeah, this one is also matched. I can just write it in this way, right? So this is fine, man. Yeah. Uh, this one, yeah. U set as well as the V set. So this one I can just write it in this way. The output that we need to get here is 1123 0123, right? So let's check the same. Let's check the same. Let me delete this one entirely. So I hope the algorithm, whatever I have to done is correct. Let's see. Let's come here. Let me give Control J. So we are considering this one base U to V and base V to U, right? So we are going with the Hopcroft.pair actually. Pair U pair. So this is fine. I'll just keep clear screen here. Python followed by file name dot py. Yeah. Maximum matching size is 4. So yeah, this is also correct, man. So we are making use of the BFS and DFS here, right? So we can get in this one. So we can just get 1 1 2 3 or 0 1 2 3. It doesn't matter, basically, right? So why? Because this one Hopcroft Karp algorithm may output either matching this one depending on the order of the iteration in the BFS or the DFS. So this part is also correct. 0 1 2 3 0 1 2 3 is also correct. And if you get the output 1 1 2 3 and 0 1 2 3, that is also correct basically, right? So that is also correct. Don't get confused here, right? So but this one maximum matching size is 4. Maximum matching size is 4. I have showed you at the end, right? Maximum matching this one is 4 basically. Right, so this is fine. Now, yeah, this is it for the Hopcroft Karp algorithm. So before moving into the next algorithm or this one, uh, next algorithm we'll be discussing on the Edmund Karp algorithm, right? So before moving on with the this one Edmund's Karp algorithm, so let me summarize whatever we have learned so far, right? So here, yeah, 1 second, just give me a second. Yeah, just try to remember these 3 or 4 points, man. Yeah, whatever I tell now. Yeah. First thing here would be Hopcroft Karp finds the maximum bipartite matching, right? Maximum bipartite matching, right? So just remember this one, maximum bipartite matching, right? So this is fine. Again, this one, what does this one Hopcroft Karp finds? Basically, it finds the maximum bipartite matching in this one because of basically square root of v into e time, right? So this is the time complexity actually. This is the time complexity, right? So this is one of the important things that I wanted to mention. Now it uses the BFS to layer the graph and DFS to augment along the multiple paths simultaneously. It uses BFS as well as the DFS. We know this one, right? Basically, why BFS here? BFS to layer the graph and DFS to augment along multiple paths simultaneously, right? So this is much faster than the simple augmenting path algorithms for the large graphs. So this is one of the advantage, right, of using the this one Hopcroft Karp algorithm, and it is perfect for the real world problems like whether assigning the jobs, right? So we call it as job assignments problems, if you remember, right? So network matching. This is also one of the use cases, right? And also pairing problems. Also, you would have come across the pairing problems as well, right? So this will be used actually. This algorithms will be used on job assignment problems as well as the network matching and the pairing problems, right? So these are the use cases I wanted to discuss, right? So this is it for the this one Hopcroft Karp algorithm, right? So this is fine, I believe. Now, next we'll be discussing on the Edmonds Karp algorithm. For now, this is it. Thanks for watching, guys.